Hello and welcome everyone again for the live session number 9 for the week 9 of the NPTEL course Introduction to Semiconductor Devices. As you know, the course instructor for this course is Professor N.K. Emani of IIT Hyderabad, and I'm your official PMRF TA for conducting these live sessions. So, as I have said multiple times, these live sessions are supposed to be interactive so that you can ask me any question, clear your doubts that you may have during your regular lectures, and we'll have a nice discussion on it. So the plan for these live sessions from my side is quite simple. In the first quarter of the session, that is in the first 10 to 12 minutes, I'll give a brief overview of the content that is being delivered, that has been delivered in this current week, so that you'll get a quick refresher, quick recap of the things covered, and that will be helpful in the problem solving later on. And then we'll move on to the assignment problems, and which are like very similar to your current set of assignments, and also the end semester or the end course exam that you'll take at the end of the course. Okay, so without further ado, I think let's get started. So we'll begin with a short review of the week 9's lecture content. So let me go to the slide number 1. Can you just confirm you can hear me well? Okay, thank you. So, as we know that in the, so far in this course we have studied different fundamentals and basics of the MOS devices basically. So, so far in this course we have studied like some fundamental aspects of semiconductor devices. First we understood how a PN junction works, and then we understood how a MOS capacitor works, which is a metal oxide and semiconductor sandwiched together, and we argued that it is at the heart of the MOS devices, and one of such devices is the MOSFET, that is metal oxide semiconductor field effect transistor. So all of that lays the foundation to understanding one of the most important semiconductor devices, which is a MOSFET. So it is not possible for us to really imagine a world which without a MOSFET basically. So MOSFET has kind of revolutionized the semiconductor industry, and it has paved the way for the modern technological revolution as well. So like it wouldn't be any exaggeration if I say that if there was no MOSFET, possibly there is no semiconductor device right now. So this like tells us that this is the information technology revolution that has happened because of the MOSFET revolution. So MOSFET is that crucial device, and that is what we are studying in this course. Okay, so if we just consider the three-dimensional picture of a MOSFET, we can see here that it is, just a moment. Yeah, so you can see that here we have the length of the gate, which is having a certain length. So this is an important terminology. The length of the gate is essentially the distance between the source and drain. So this is L effective, and we already told you that the essential physics happens only about few micrometers here. So particular this is few microns only. So this is the important crucial part, and below this is just a bulk semiconductor. So this is how a three-dimensional MOSFET structure looks like, and so you can see that these are the black dots here, which are actually nothing but the contacts for the source and drain. And the reason is if you look at the semiconductor, we talked about some metal and semiconductor junctions, so Schottky junctions. they can be rectifying contact or ohmic contact, as we say. So it is not enough to have a piece of semiconductor, but we have to connect it to the external world, right? So we have to connect it, relates it to another transistor. How do we connect? So if you directly put a piece of metal, it will have a contact resistance. We have mentioned this earlier also. So now to avoid that, we can engineer these contacts in such a way that one contact would suffice, but we just typically makes more contacts to minimize the contact resistance. So this is basically how a MOSFET structure looks like. This is the length, this is the width, these are contacts, gate, and the substrate. But how it actually operates is the main question that we try to answer in this particular week. So the current in a MOSFET is basically due to the flow of charge in the inversion layer or the channel region adjacent to the oxide and semiconductor interface. So this region basically, or if you consider this is the region that is the crucial region for the MOSFET working. And we have discussed the creation of the inversion layer charge in the enhancement type MOS capacitors in the previous weeks. So we may also have depletion type devices in which a channel already exists at zero gate voltage. So if we talk about the MOSFET structures, there are four basic MOSFET types, two for N type and two for the P type. So the figure on the left here shows that N channel enhancement mode. So this is N channel enhancement mode MOSFET, and you can implicit in the enhancement mode operation is the idea that the semiconductor substrate is not inverted directly under the oxide with zero gate voltage, and a positive gate voltage induces the electron inversion layer, which then connects the N type source and N type drain. So this particular channel is created in the enhancement mode. Okay, the source terminal is the source of the carriers that flow through the channel to the drain terminal. For this N-channel device, electrons flow from the source to the drain, so the conventional current will enter the drain and leave the source. So the electron move from this to this side, but the conventional current is opposite of the electron flow as we know it. And the conventional circuit symbol for the N-channel enhancement mode device is also shown here. So this is the circuit symbol. And the adjacent figure here, that is the right figure here, shows an N-channel depletion mode MOSFET. An N-channel region exists under the oxide without even applying the bias to the gate. So 0 volt applied to the gate. However, we have shown that the threshold voltage of a MOS device with a p-type substrate may be negative. This means that an electron inversion layer already exists with zero gate voltage applied. Such a device is also considered to be a depletion mode device. The N channel shown in the figure can be an electron inversion layer or an intentionally doped N region. The conventional circuit symbol for the N channel depletion mode MOSFET is also shown here. So let us go to the slide number 2. So when we do this, we get two types of characteristics. So the MOSFET IV characteristics I have just summarized here. The first type of characteristics is called as the output characteristics, which is essentially a function of a plot of drain voltage versus the drain current. Drain voltage versus the drain current. And sometimes we also call this as ID-VD characteristics, the drain current and the drain voltage characteristics. Okay, and we have seen this in detail. We fix a particular gate voltage and then we sweep the drain voltage from 0 to some maximum value, and we see how the VDS, how ID basically varies. So while we do that, we saw that when the drain voltage is small, your MOSFET is biased in linear region, and then as you cross the saturation voltage, that is VD sat here, which we said that is equal to VGS minus VT. So VD sat is VGS minus VT. If your drain voltage is greater than VD sat, we say that the current saturates. And we have also shown here two particular graphs. The one is basically when your gate voltage is less than VD, we do not expect any current here. So this is the one. And the second is the case where VGS is equal to VDD. In that case, the saturating current characteristics is shown here, where it is important to note that on the left of the VD side it is the linear region, and on the right side it is the saturation region. So this is one type of characteristics which we call as the output characteristics. There is also one more type of characteristics on the right. You can see here it is nothing but the transfer characteristics, in which in this case we will keep the drain voltage fixed, that is VD fixed, VDS is fixed, and then we sweep the gate voltage VGS and see how our drain current varies. Okay, so when we do that, we can choose the drain voltage to be a smaller value like few millivolts, and if we do that, the MOSFET will be biased in a linear region. So you get a linear transfer characteristics, which is shown in the figure here, and then you could also choose the drain voltage to be at supply voltage, that is VDD. If you choose that, then definitely the VDS is going to be greater than VD sat, that is VD saturation, and that is why the MOSFET will be biased in saturation. So you get a ID VG curve. So in the transfer characteristic, we are fixing the VDS and then sweeping the VGS, as I said. In the output, we are doing the opposite, in which the VGS is fixed and we sweep the VDS. So these are the characteristics for the particular MOSFET. These are helpful in the measurement of the uh, different parameters of the MOSFET, different metrics. So we can get family of curves for different fixed voltages. That is we have seen in the lectures as well, based on the quadratic behavior in the saturation region. So this is for an NMOS device. We could also have it for the PMOS device, and we said that the PMOS device is essentially complementary to the NMOS thing. Okay, so I think this is about the IV characteristics. Let's move to the third slide. So to summarize, this week was basically devoted to understanding the physics and characteristics of the MOSFET. The MOS structure was assumed to be ideal, and considerations were limited to the basic transistor configuration only. And when a MOSFET is biased into inversion region, the induced surface layer forms a conducting channel between the source and drain contacts, as I mentioned in the slide number 1. The greater the applied gate voltage in excess of turn on, the larger the conductance of the internal channel at a given drain voltage, and a non-zero drain voltage in turn initiates the current flow between the source and drain. The current flow is proportional to VD at lower drain voltages, and it slopes over due to the narrowing of the channel as VD is increased, and eventually it saturates once the internal channel vanishes or so-called pinches off near the drain. So a summary of different formulae for all of this is given in this slide. You can see here. So the drain currents uh, are given, which are as a function of the mobility, the oxide capacitance, and different applied voltages like VGS and the threshold voltage, VDS as well. So you can simplify this particular relation. If we have smaller values of VDS, we can neglect this particular term and we get this drain current as equation number 2 here, where Kn is a common factor substituted for Wkn star by Wkn prime by twice L. Also, the peak current occurs when VDS is equal to VD sat, as we saw in the figure as well, the graph as well. So VD sat can be given as VGS minus V threshold. For VDS greater than VDS saturation, we saw that the ideal current is constant and is given by this particular value, that is ID saturation. When VDS becomes very large, as compared to the VD saturation. Also, there are a couple of parameters. One is the MOSFET transconductance, which is defined as the change in the drain current with respect to the corresponding change in the gate voltage. So GM can be given as DABA ID by DABA VGS. Similarly, when the MOSFET is operating in the non-saturation region, GM can be shown here in equation 6. We have just differentiated with respect to VGS the ID value, ID function. Going to the final slide, the MOSFET substrate bias is summarized here. So the change in the threshold voltage due to substrate bias is given by this relation. So delta Vt is given, where a gamma is called as the body coefficient, given by this particular equation number 9. So I think this is all about the summary of this week, and let us directly move to the assignment problems. So let us start with the problem number 1. So the problem is as follows. I'll just read it out for you. Consider an n-channel MOSFET with the following parameters. The parameters are given for our reference. First is the Kn prime, next is the ratio of the width and length given as 8, and next is the threshold voltage. We need to find out the drain current when VGS and VDS are given by these particular values. One thing we can note straight from these two values, basically these two and this value, that our VDS is larger than the difference of VGS and VT. So our VDS, which is 1.2, is larger than the difference of VGS, that is 0.8 minus 0.4. So this particular condition, it tells us that the device is in saturation. So the saturation condition has been satisfied here. That means we can use the saturation equation for the ID value. So ID in the saturation region is given by mu times Cox. Mu is the mobility, Cox is the oxide capacitance, then W by twice L. W is the width and L is the length of the MOSFET, and VGS minus VT bracket squared. So this particular equation we can directly use. Here the parameter Kn prime we can substitute for the product of mobility and the Cox, and this particular parameter is called as Kn prime is nothing but the process transconductance parameter. It is process transconductance. Okay, so let's just substitute all these parameters here. Mu Cox, which is nothing but Kn prime, is 0.18 milliamp per T squared, and W by L is, I think somebody has just typed the answer. I'll just substitute and write the answer as for you as well. Let me just write it for you. 8 by 2 times VGS minus VT is 0.4 squared. So we get the value of ID as 0.1152 as correctly mentioned by Kyle R. So the answer is 0.1152. Okay, so this is the straightforward question. Let's move to question number 2. So this is again a common data question for question number 2 and 3. The IV characteristics of an N MOSFET are shown here, and we are supposed to answer a couple of questions based on these characteristics. The question number 2 is the on current, that is ID on, is approximately. So the on current is asked based on the plot of IV characteristics. So we know that the on current, ID on, corresponds to the current when VDS VDS is equal to VGS, and which is equal to the supply voltage, that is VDD. So ID on is when this particular condition is true. So let us go to the graph and see where this is true. So VGS and VDS, so VGS is 1.8 volt corresponding to VDS is 1.8. So this is the point where our condition gets satisfied, that is VDS is equal to VGS equal to VDD. So our ID, which is ID on corresponding to this point, is 0.3. So our ID on is 0.3 milliamp. So answer is this. Similarly, the question 3 is for the ID off, and ID off is also, we know that the ID off is corresponding to ID when the VGS is equal to 0 and VDS is equal to VDD. So let us check the graph. We want VGS to be 0. So VGS to be 0, okay. And also we want VDS to be equal to VDD. So VDS equal to VDD in our case is 1.8 volt. So this is the graph. So these two conditions satisfy at this particular point. So this is the ID of it. On the log scale we can see it clearly, but here also we can see that it is around 2 times 10 to the power minus 11. That is nothing but, so yeah, 2 times, yeah, so that means 2 times 10 to the power minus 11, that is 20 times 10 to the power minus 12 amp, which is nothing but 20 picoamp. You can see 1 picoamp is 10 to the power minus 12 amp. So our answer is 20 here. Okay, let us move to again a common data question for question number 4 and 5. This is also a simple question. Question is as follows: the ID versus VGS characteristics are shown in the figure, and these are determined experimentally for an N-channel MOSFET. And the width and length of the MOSFET is given by 15 and 2 micrometers respectively, and we can assume the drain voltage to be 0.1 volt and the oxide capacitance as around 7 times 10 to the power minus 8 farad per centimeter squared. So the fourth question based on this data is the mobility of the carriers in the inversion region is. So the mobility is asked, and similarly the fifth question is the threshold voltage for the MOSFET is. So basically we want to find out the threshold voltage, Vt, and mobility, that is mu. So if you just look at the figure here, you can see that the ID values for two particular VGS are also given. So for VGS 1.5 and 2.5, ID values of 35 microamp and 75 microamps respectively are also indicated in this particular figure. So if you just write down the values, the equation for ID, which is nothing but mu times C ox W by L VGS minus VT times VDS minus VDS squared over 2. So we can have two equations here, because for two different values of ID and two different values of VGS we can have two equations, and we have two unknowns, like mobility is unknown and also the threshold voltage is unknown. So two equations, two unknowns. So I think this is enough information so that if you have two equations we can find out two unknowns from those two equations. So what, I'm not going to solve this particular problem here, but I'll just give a small hint. As you can see, so if you just simplify this particular equation as shown in the hint also, that the VDS squared term can be ignored because VDS is a small value. So we can first simplify the relation, and we can write the value of ID as W mu n Cox over L times VGS minus VT times VDS. And as I told you, for two values of ID, we can just write it as, we can just simply write ID2 minus ID1, which will be equal to W mu n Cox over L VGS2 minus VGS1 times VDS. Okay, if you just substitute it, ID2 minus ID1, that is 75 minus 35 times 10 to the power minus 6, where W by L is 15 by 2, and mu n, which is our unknown, and Cox is around 7 times 10 to the power minus 8 times VGS2 minus VGS1, which is shown here is 2.5 minus 1.5 volt, and our VDS is 0.1. If you just solve for mobility mu n, you get the value of mobility as around 770 centimeters squared per volt second. So mu n is around 770. Okay. Now once we know one parameter, we can substitute the value of mu in this particular equation. We will get the value of mobility, and that I'll directly write as, we'll get the value of Vt. As we know mobility, we can find out Vt, and that value comes out to be around 0.625. So the answer for fifth question is 0.625. Okay, so I think this was also quite straightforward. So let us move to the sixth question. The question is again a common data question. A silicon MOSFET has the following parameters. Its doping concentration, thickness, and the epsilon values are given. Also the Fermi potential is given here, and we want to find out the body coefficient. So as we just touched upon in the summary slide, the body coefficient is the one which is to be determined here. So as we have in our summary slide, let me just go it. The delta Vt value is, I'll just write it here, delta Vt, which is gamma, okay, which is gamma, our body coefficient, body effect coefficient, times the so we know that the gamma is nothing but square root of 2 times charge times the epsilon of silicon and the Na divided by the oxide capacitance. Just mere substitution again here. So 2 times the electronic charge, that is 2 times 1.6 times 10 to the power minus 19 coulomb, times the permittivity, that is 11.7 into 8.85 into 10 to the power minus 14 times 10 to the power 16, which is Na, and divided by the oxide capacitance, and oxide capacitance is epsilon of oxide divided by the thickness, as we have seen in the previous sessions as well. So let me write it here as well. 3.9 times 8.85 times 10 to the power minus 14 divided by the thickness of the oxide, that is 12 nanometers, which is nothing but 12 into 10 to the power minus 7 centimeters. So if you just calculate it, we'll get the value of body effect coefficient gamma as 0.2. Okay, again based on the same data, we want to find out the change in threshold voltage for Vt of 0.64 and Vsb of 2 volt. So in the previous slide I wrote the equation. So again here we just need to do a mere substitution. So let me do it again here. Delta Vt is gamma times, gamma is 0.2 that we determined in the last problem, gamma times the square root of 2 times phi f, that is 2 times our Fermi function, that is 0.3473 plus Vsb, that is 2 volt, minus 2 times again the Fermi function, Fermi potential, that is 0.3473. Okay, again if we just later calculate it, you will get the value of change in threshold voltage for Vt naught of 0.64 is 0.16. It is rounded off. Okay, so let's go to last couple of questions now. The question number 8 is I've taken it from previous gate exam, EC gate 2016. The question is as follows: consider a long channel NMOS with source and body connected together. Assume that the electron mobility is independent of VGS and VDS. Okay, so this mobility we can take it as a constant. Different parameters are given, GM and GD, for different values of VDS and VGS. And we also know that the GM is nothing but the dabba ID by dabba VGS, and GD is nothing but dabba ID by dabba VDS. Now they have asked is the threshold voltage of the transistor is. So threshold voltage Vt is asked, and based on this thing we can write that we know that the GM, that is nothing but dabba ID by dabba VGS. If we just go to our summary slides, GM, which is nothing but dabba ID by dabba VGS, is given by this particular relation. We can directly substitute here mu times C ox W over L VDS. Okay, so GM is given as 0.5 micron, so 0.5 times 10 to the power minus 6, which is equal to mu, which is our mobility. So let us keep it as it is, mu. C ox is also not given, so let it be as it is, W by L. I think these are constants, and for VDS of 50 millivolt times 50 10 to the power minus 3 volt. So this is one equation. Let us call it equation number 1. Similarly, we know that the GD value, which is nothing but dabba ID by dabba VDS, is given by the following relation. So we just need to differentiate ID with respect to VDS. So we'll get it as follows. VGS minus V threshold minus VDS. So GD is given as 8 micron, so that is 8 times 10 to the power minus 6 equal to point. In this case, we will consider VDS to be 0. So this particular thing, for VDS is equal to 0, what it becomes is 0.5 times 10 to the power minus 6 divided by the 50 times 10 to the power minus 3, 2 minus VT. So VDS is 0, so VGS is 2 volt here, 2 minus VT. We'll solve for VT and we'll get the value of threshold voltages. Just minus 6 gets cancelled and we'll get 2 minus 0.8, which is nothing but 1.2 volt. Okay, so what we have done is we have just substituted this value from equation number 1. Okay, so is it clear? Do you have any doubt in this? Okay, if no, then I'll move to the last problem. So this is again from the previous gate course, gate exam. Basically, the drain current of a MOSFET in saturation region is given by this particular relation where K is a constant. Okay, the magnitude of the transconductance GM is, okay, so we have seen it already that GM, which is the transconductance, is given by dabba ID over dabba VGS. So I think this is quite straightforward. The ID value is given, we just need to differentiate it with respect to VGS and that will give us the transconductance GM. So let's do it, and if we just differentiate it with respect to VGS, we'll simply get 2 times K, which is a constant, VGS minus VT times its coefficient, that is 1. So 2K VGS minus VT. So the answer for this question is this. Okay, so the questions are over, but I have one more bonus question to discuss and then we'll wind up the session. Okay, so the bonus question is as follows. This is also like formula based. The objective is as follows. Design the width of a MOSFET such that a specified current is induced for a given applied bias. So we need to design a MOSFET such that the current, the specified value of current is induced, provided we have a particular bias. Okay, different parameters are given. Consider the n-channel MOSFET first and foremost, with the parameters as the length, mobility, the oxide capacitance and the threshold voltage. And we need to design the channel width W such that the ID value, that is 4 micron, ID saturation value actually, for VGS of 5 volt. So we need to find out the width such that all these parameters fit in. Okay, so we know that for the transition biased in the saturation region, we have the saturation current, that is ID saturation, as nothing but W, which is the width of the MOSFET, times the mobility times the oxide capacitance divided by the 2 times the length of the MOSFET, length of the channel actually, times the difference of VGS minus VT squared. Okay, so if you just substitute these parameters 4 milliamp, 4 times 10 to the power minus 3 times W, and the mobility is 650 centimeter squared per volt second, times the oxide capacitance, which is nothing but 6.9 times 10 to the power minus 8 farad per centimeter squared, divided by the 2 times the length, which is 1.25 micron, that is 1.25 times 10 to the power minus 4 centimeter. We need consistency in the units. Also the VGS is 5 minus VT, which is 0.65 volt squared. So we have only one unknown here, so we can solve for it and we'll get the value of W as 11.8 micrometer. Okay, so one thing to note here is that the current capability of MOSFET is directly proportional to the channel width. So the ID such is directly proportional to the channel width W, and the current handling capability hence can be increased by increasing the value of W. So this is one thing to note, and with this I think this is a good time to close the session. If you have any doubt, you can stop me. Okay, so for question number 6, do you have doubt in question number 6? Okay, for question number 6, let me go to okay, the question is, just a moment, for sorry, in question number 6, question 5. Okay, in question number 5, for finding VT, which drain current we substitute? No, basically what we have done is we have used this particular graph in which we have two values of IDs corresponding to two different values of VGS. So we have then made two equations and we used both the values of IDs corresponding to different corresponding values of VGS. So we used both values of IDs, we can so to say, and we then just subtracted equation number 1 and equation number 2, which correspond to one value of ID. So for one value of ID, which corresponds to, let's say, 2.5 volt, we will get one equation. Similarly, for another value of ID, we will get the another equation. When we subtract those equations, that is ID2 minus ID1 for VGS2 minus VGS1, we'll get this particular relation. So if you substitute ID2 and ID1, which corresponds to VGS2 and VGS1 values, we'll get the value of, we can determine basically the mobility, and once we have the mobility, we can use any of the equations. Then if we have two equations, in any of the equations we can, because mobility is constant, and we can use any of the ID equation, and that will satisfy for both equations actually. So there is no particular ID no particular drain current, because it will satisfy for all of both of the equations. Is it clear? Okay, thank you. Okay, so this brings me to my final slide. I would like to thank all of you for joining for this live session, and I hope to see you in the next live session, that is for the 10th week on Friday at 6 p.m. 30th September. Meanwhile, you can go on my YouTube channel where these recordings would be shared, and you will see these recordings. You can follow it. If you have any doubt still, you can ask the questions on the comments section or also on the discussion forum of the NPTEL-ISD course. Okay, so I think that's it from my side for this particular live session. I hope to see you on the Friday at the 6 p.m. Have a nice weekend. Bye bye.